Okay, we are back. This is still the introduction to the finite projective plane. And I left up here the list of things. I rambled for 10 minutes about who I am and what I'm doing and why. I mentioned that we would eventually talk about the finite projective plane. I rambled a little bit stupidly about whether we should possibly consider geometry to be finite or at least discrete in a certain kind of sense. I reviewed sort of basic axiomatic geometry, traditional ancient Greek axiomatic geometry of Euclid, and how it was a little bit vague about whether we were supposed to begin with the points or whether the points were understood to be already there or something like that. We discussed the universe of constructible points. This is the infinite but countable, if you know what that means, collection of points which you can create, starting with 2 points and using only a straight edge and compass. I kind of very loosely and poorly explained why we might care about these finite geometries. I rambled for a long time about the various revolutions in the American mathematics education curriculum, and shared personal anecdotes which might be only of interest to my own students and maybe not even them, about the origins of this approach to teaching geometry, where you actually begin with the finite and discrete, looking at it extremely rigorously before expanding to what you might think of as normal geometry, in which every line contains an infinite number of points, or maybe even an uncountable number of points. Those are sort of advanced concepts. So perhaps we understand the finite first, and then we understand things involving real numbers. Well, this is a discrete math class, so that's our approach. And then I spent, I don't know, half an hour or something going into extreme detail about this unit on affine geometry that was part of the magnet geometry curriculum a long time ago and is no longer. Why did I spend so much time on this? Well, it is very similar to the geometry that we are going to study now, except our geometry is still finite. It's still axiomatic in the sense that we're going to start with very explicit axioms governing the relationships between points and lines in our plane, but it is projective. So what is projective? Well, in a perfect world, we would also then understand what is projective geometry. That's not something that probably any of you know about. And you don't absolutely have to know anything about projective geometry, but it certainly helps. And I knew only the most loose possible facts about projective geometry in every other time that I have ever taught discrete math. But in the last 12 months, something very exciting happened, which I taught a course called Advanced Geometry, which ran exactly a year ago in the spring 2019. And our textbook was this book called Geometry Revisited by H.S.M. Coxeter. And we learned all about projective geometry, and so I now kind of know it, although not as much as an expert would or should. And this class is running next year, assuming we have school and stuff, so some of you who are juniors could take it in the fall of next year. So I'm going to give you a preview of some things that we're going to learn in that class, and by doing that, explain what projective geometry is, and then finally come back to our real subject, which is finite, axiomatic, projective geometry. Alright, what is projective geometry? Well, without trying to answer that question right away, let's just go to an example. So I have an example for you. It's called the Theorem of Papus. And okay, when I Google that, I don't get what I want. So maybe the Theorem of Papus is usually, that name is usually associated with Papus's theorem about rotating some object about an axis, and the volume is the centroid or whatever times the distance that it travels, or something like that. The area of a cross section times the distance traveled by the centroid of that shape. So no, I'm not talking about that. I'm talking about what some people call Papus's hexagon theorem. That's not what my book called it. But anyway, what does it say? All right. And Papus is ancient Greek. mathematician. So this is he's I believe in the same time period as what's his name? Archimedes. And so he's part of the one of the last couple of generations of sort of really advanced Greek math and science, post Euclid. Okay, and he does a lot of things, and so that gives you an indication of how old the sort of ideas, at least, of projective geometry are. Okay, what is the Theorem of Papus? It's very difficult to explain and to understand why you should care about it, but nonetheless, we begin. So imagine you have two lines, and I think it doesn't matter whether these lines are parallel or intersecting. I think it's irrelevant. So you have two lines. And now, let us form a hexagon, and I use hexagon with air quotes because a normal hexagon, you might say, is going to look like this. And it's a polygon, and it has all those kind of polygon properties. Like every edge connects two vertices and they don't cross and all that kind of stuff. And in fact, we have, I'll label the size of this hexagon A, B, C, D, E, F. And yet, fancy people or crazy people will also use the word hexagon to refer to simply any cycle, to use the graph theory term, of length 6, wherein perhaps the edges are crossing each other in some kind of chaotic fashion. So if you just do like 1, 2, 3, 4, 5, and then I messed up 6, that's a hexagon in a certain sense, in that it has 6 vertices, 6 edges. Every edge connects 2 vertices, and yet we make no claim about the object being convex, or even that the edges don't cross each other. So, okay, if you're okay with this being a hexagon, then this theorem says create any hexagon out of points on create any hexagon of points such that every other point is on one of the different lines. So, okay, so I don't know, call this like L1 and call this like L2. So let's just start, and there's a good way to do it. Okay, yeah. So start with this being point A, and let's let the second point of our hexagon be B. I'm going to stick with this convention. And then the third point be C, so bouncing over to the other line. Then the fourth point be D, coming back over here. So A to B to C to D to E to F. Okay. And yeah, good. I'm going to draw this now, but I want to draw it in a way that highlights, that previews the theorem I'm going to make. So I want to draw it in such a way that opposite sides of the hexagon, and by opposite sides I mean, A, B, E, D, B, C, E, F, which you would typically in a normal hexagon call opposite sides, are depicted with the same color. So I just want to sort of show you that, right? I go from A to B, so that's purple. Then I go from B to C in green. I hope this shows up on the camera. It will a little bit. From C to D in red. But then DE is opposite to AB, so I'll switch back to purple. What did I say? AB is opposite to ED, so I'll go to purple. And so I would like to call ED and AB opposite sides of this hexagon. And then I just keep going. A to B to C to D to E to F, which I will do in green. And then from F to A, back in red. Okay, so that completes the hexagon. Okay, so what? The Theorem of Papus says that take opposite sides of this hexagon, they will intersect. That's always true because I start on the line and I'm always bouncing around to different sides of the line. And so if it's a hexagon, I guess, let's see, what's the way to do this? If I start on line 1, then I go to line 2, then I go back to line 1, then back to line 2, then back to line 1, then back to line 2, and so sort of every other point is on one of the two opposite lines, and therefore, let's see, what to say here. Therefore, therefore two opposite sides are always going to be sides which, two opposite sides of the hexagon are always going to be sides which are connecting a point on one line to a point on the other. Why must they intersect? Well, they just do intersect, I guess, because A to B and D to E. Yeah, because any two lines, well, okay, I'll hold off on that for a minute. Here, at least, in this most simple example, they do intersect. So I'll put a big purple dot here at the intersection of those two opposite sides. But then opposite sides AF and CD also intersect. So that's put a red dot there. And then the other pair of opposite sides, what's left? EF and BC also intersect. And there is a fact here, which I think is somewhat, at least plausible from my hastily drawn picture, which is that these 3 points are collinear. Okay. So that's the theorem of Papus. It says, start with two arbitrary lines, create a hexagon based on points which are on those lines, in which every other point of the hexagon is on a new line. Connect points which are on, connect the intersections of pairs of opposite sides of that hexagon, and those 3 points of intersection will be collinear. Okay, you can prove this, I'm not going to do this. And note that the spirit of this theorem is one which is sort of independent of distances or anything like that, right? I don't care anything about these lines. I don't know where they are. I don't know whether they're parallel or intersecting, these lines L1 and L2. I don't know or care what angle they make with each other. I don't care where A, E, and C are on these lines, whether they're close to each other or far from each other. I don't care anything about the angles between any of the geometric objects in this figure. This is somehow a pure theorem about incidence. And what is incidence? Incidence is a sort of advanced term which refers to whether a point is on a line or not. And here, the only thing going into this theorem is that these points A, E, and C are sort of on this line L1, and that B, D, and F are on L2. So that's an example of incidence. A point being on a line is called an incidence relation. And then the fact that these lines intersect is a fact of incidence, and the fact that these lines are collinear is just another way of saying that, well, if you take the line through the purple dot and the red dot, that the green dot is on that line. So statements about 3 points being collinear could be rephrased as a statement about a certain point being on a certain other line. And so somehow this arrangement of objects implies that these 3 points are collinear. This is a pure theorem of incidence. And now you can feel free to just move these objects around in all kinds of crazy ways, and you will still find that the theorem holds. And in fact, we're going to do 2 more of these. Here's one. Here's one. So I have now, again, 2 lines, but now I'm going to, so I'll take A to B. So I'm going to just now do like this. But now notice that I'm choosing a little bit differently so instead of here I did a kind of a cross. This is the easiest one kind of to understand. But now I'm going to go to A to B to C. I hope I'm doing this right. And then to D. And then to E. And then to F. And then back to A. Okay, and so now perhaps we need some arrows or something to follow what's going on. It's like this way, then this way, then this way, then this way, then that way, and then finally that way. So that's the hexagon. Okay, well now what does this theorem say? It says, okay, once again, connect opposite sides of the hexagon. Well, how can we do that? A, B, and ED are opposite. So here's A, B, and ED. But now notice that A, B, and ED don't appear to intersect. Okay, but really all lines like intersect or something, man, because this theorem was not about the segments ED, but was in fact about the lines A, B, and ED. So this is another way in which we are sort of taking a more abstract view of things. And okay, that looks sort of okay. I could have put more thought into this picture. What's the next one? B, C, and E, F. B, C, and E, F also intersect, not the segments don't intersect, but the lines through B, C, and F do intersect. So this point is the intersection of one pair of sides of the hexagon. This point is the intersection of another pair of sides of the hexagon. And finally, B, C, and F, C, D, and A, F. And C, D, and A, F actually intersect. And okay, this picture's a little bad, which is why I was worried I was going to run out of board space. So now let me try. I think it would be more like that where they intersect. Okay, and so now the 3 points of intersection are these 3 points. And do they appear to be collinear? Okay, that's like plausible. In other words, the theorem is applicable not just to the points of intersection of the sides of the hexagon, so to speak, but the points of intersections of the lines through those points. Okay, and now maybe you see where this is going. So for my third and final picture, I will draw another arrangement of the Papus' hexagon theorem. But now I'm going to do it in such a way that something crazy happens. Okay, so try not to mess this up. And now I will start here at A. But I will explicitly draw this line to be sort of perpendicular. Although maybe that's against the spirit of projective geometry because that doesn't mean anything, I'm not really sure. So then we have this point B. Now I'm going to go up here to point C, which I'll do sort of arbitrarily. And so that's C. And then for D I'll go back down here. But now, when I go back up to E, I'm going to do it once again perpendicularly. And actually it doesn't need to be perpendicular, but what I've done is I've drawn ED and AB in such a way that they're parallel. And then we go back to F, and then over to back to A again. Okay, that was a little bit poor. Shoop. Okay. Okay, so now if we're becoming kind of experts on this, what have I done? From A to B, from B to C, from C to D, from D to E, from E to F, and from F back to A. Okay, what are opposite sides? Perhaps I should have kept this color convention going, but okay, too late. A, B, and E, D, well, let's skip that one. Let's go B, C, and E, F are opposite sides. So that's B, C, and that's E, F. Okay, well, once again, to find the intersection of sides B, C, and E, F, I need to extend beyond. So that's my first point of intersection. Let me do this in purple. That's the intersection between opposite sides of the hexagon. Another one is CDAF. So CD and AF, these two actually intersect. And now, man, it doesn't look so, it didn't work out as well as I hoped, but okay, whatever. Now finally, we do sides A, B, and DE. But now do you see that there's somehow kind of a flaw or something in the Theorem of Papus? Because the Theorem of Papus says that opposite sides of a hexagon, the intersections of the points of opposite sides of the hexagon will be collinear. But A, B, and ED in this case, which are opposite sides of this hexagon, are parallel. And so they don't intersect. And so you're kind of left sad or something, because you have this line going through the 2 points of intersection, and it wants to go through the third point of intersection. But where is the third point of intersection? It's the intersection between A, B, and DE. And yet, there is no point of intersection in the traditional sense, because they're parallel. so you could sort of put an asterisk on this theorem which says, okay, well, if happens to be that a pair of sides of your hexagon are in fact parallel to each other, then the line through two of those points will be parallel to, and I think hopefully on this diagram it appears to be true, that this line is parallel to A, B, and DE. But everything becomes a lot more elegant and simple if you just are willing to kind of shrug and say, well look, A, B, and DE, they're parallel. But even though they don't meet technically, they kind of meet each other. They meet each other like very far away, like infinitely far away. And so let's just let's just extend the notion of intersection such that any two pair of parallel lines in fact does intersect, but intersects out at infinity. And if these two lines intersect out at infinity, A, B, and DE, and in fact any line which is parallel to A, B, and DE also intersects out at infinity, then the theorem just holds, because now the point of intersection of A, B, and DE is this point at infinity that this purple line also goes through. Okay, so this is an example of why somehow you achieve a greater level of clarity and unity in your geometric thinking if you just force all parallel lines to actually meet. This is the nature of projective geometry. This is my sort of idiosyncratic introduction to the idea of projective geometry. What is projective geometry? It's a geometry without distances, without notions of how far any 2 points are from each other, without notions of angles or anything like that. We don't care about things like that, the metric, so-called metric properties. We care only about the incidence relations. Which points are on what lines, and which two lines are, which points are collinear with each other, and things like that. And in fact, in a projective geometry, if you have a bunch of lines which are all parallel in the traditional sense of pointing in the same direction, well, if you extend these lines out sort of very, very, very far, maybe it was best to draw them looking actually parallel. So parallel, parallel, parallel. These three lines are parallel. Well, traditionally you would say, in a normal Euclidean geometry, you would say that these three lines never meet. But in projective geometry they do meet, but they meet at the horizon, so to speak, at a point at infinity. And so there's this horizon line, and this sort of horizon line serves as a point, or is this sort of special line at infinity or something like that, that pairs of parallel lines meet at. And what's interesting is if you have a different three pairs of parallel lines, these are in purple, so these three are all parallel to each other, but they're not parallel to these three, then they will also meet at a point at infinity. But they'll meet at their own special point. In other words, if you imagine yourself, and this is something that is taken from the art of the Renaissance, that if you are trying to draw things so-called in perspective, then you have to learn all these principles of how to accurately reflect. One of the first things I remember learning in 7th grade art class is that when you draw, lines that are supposed to be parallel on the paper, you have to show them sort of meeting at a point on the horizon. But if you turn your angle to a new and look in a new direction, then those lines will also meet. This is called like a two-perspective picture or something like that. Don't know anything about this really. And so somehow there is a point at infinity for every possible pair of parallel lines. Or not pair, for every possible collection, or you might say equivalence class of parallel lines has its own point at infinity where they all meet. And there's the horizon, which is the kind of line through all those points at infinity. Alright, this is basically projective geometry. Alright, after doing all this, finally, I will unify these two things I've been talking about for an hour and a half, finite axiomatic geometry and projective geometry, and we will do finite projective geometry. And in particular, we're going to do, in this class, we're only going to look at the two-dimensional version. And so the two-dimensional version of finite projective geometry is called the finite projective plane. And the finite projective plane is just like the affine plane that we saw an hour ago, but now projectively. And so now, in this finite projective world, we have points, and we have pairs of parallel lines, but in fact, in projective geometry, there are no parallel lines. All pairs of parallel lines meet, and they meet at a point at infinity, which loosely speaking, you can think of as being the point on the horizon where any pair of parallel lines will eventually converge. But that's just a kind of a way of understanding it. The math doesn't care about the visual representation. The math just says that in a finite projective plane, there are no parallel lines. In other words, any pair of parallel lines meet. And I think this is a way now of understanding the axioms. And I'll now briefly mention these axioms and talk about them a little bit, and then we'll end this video and we'll go to the pre-recorded stuff from last year. What is FPP1? FPP1 says through every two distinct points, there is exactly one line. This is entirely to be expected. This is taken pretty much straight from Euclid. Given any 2 points, there's a line. In some ways, this characterizes or begins to characterize the relationship between points and lines. What is a line? A line is a sort of a thing that connects points. What are points? They're things that live on lines. What is the relationship between points and lines? Well, one of the key relationships is that given any 2 points, there's a line through them, and there's only one. Okay, so far, that's very familiar. But then, out of nowhere, if you've not done any projective geometry before, comes a strange and crazy axiom, FPP2. And FPP2 says that, well, it's the exact same thing as FPP1, though you just change the word points and lines. Through every, well, you don't usually say through every, what you say is every two distinct lines meet at exactly 1 point. And this is initially perhaps a little bewildering because you probably think of some lines as meeting at a point if the lines intersect. And I guess we're familiar with the fact that 2 lines can't meet at 2 points because that would violate the previous axiom. But you're also used to perhaps 2 lines being parallel and therefore not meeting. But okay, in projective geometry, there strictly speaking are no parallel lines. Parallel lines meet at these points at infinity. Okay, and so now we can just say that every 2 lines meet at a point. Exactly 1. Okay, and what's sort of brilliant about this is that now we make no distinction somehow in these 2 axioms between points and lines. Through every 2 points, there's exactly 1 line. Through every 2 lines, there's exactly 1 point. And so there's this thing called point-line duality, in which anything that's true about points is true about lines as well. And if you're willing to state these less colloquially and more formally using the word incidence, then they are in fact exactly the same. FPP1 can be rephrased as every 2 distinct points is incident with exactly 1 line, which is the fancy way of saying is on exactly one line. And FPP2 can be rephrased as through every 2 distinct lines, or every 2 distinct lines is incident with exactly 1 point, which is a fancier way of saying goes through. Okay, and finally you have FPP3. What's FPP3? FPP3 says FPP3 is the axiom which explicitly guarantees that our plane has some stuff on it. So to bring everything full circle now, This axiom says, given any 2 points, there's a line, and allows you to create a line through any 2 points. This axiom says through every 2 lines, there's always a point. So it allows you to create a point, so to speak, if there are already 2 lines. But we need an axiom that ensures that there's something there at all. And that's what FPP3 does. FPP3 says that this model is not trivial. And what it says is there are 4 points, no 3 of which are collinear. No, there are 4 distinct points, no 3 of which are collinear. I think that's basically an exact explanation of FPP3. I hope I'm not misstating it. There exist 4 points, no 3 of which are on a common line. Okay, and what does this do? Well, it says, FPP3, that you're guaranteed to have some 4 points such that there can't be any line that goes through 3 of these points. Okay, so what does that actually mean? The best way to think about it is that the power of this axiom says that some other degenerate cases are ruled out. This is the last thing we'll do. So what's one possibility? Well, if you only had FPP1 and FPP2 and you didn't have axiom FPP3, then this says through every 2 distinct points there's exactly 1 line. This says through every 2 lines we need exactly 1 point. So consider a model or a geometry with no points and no lines. If there are no points and no lines, then I claim that model is a kind of a silly model, a trivial model. It does satisfy, however, FPP1 and FPP2. Because through every 2 points there's exactly 1 line. Well, there are just no points. So that's trivially satisfied. Through every 2 lines, well, there are just no lines. So it's automatically true. Okay, so this is just dumb. And you can't say much about a geometry in which there are no points and no lines. So we rule that out by FPP3 insisting that there are some points. Similarly, what if you just had a model with 1 point and no lines? Okay, well now, once again, you just have 1 point. Well, through every 2 points, well, there are 2 points, there's only 1, so automatically this is satisfied. And here there are no lines, so this is satisfied too. So that's ruled out. Or this model would satisfy FPP1 and FPP2, but doesn't satisfy FPP3. And we can just keep going with this, right? What if you had 1 line? So 1 line and no points. That also trivially satisfies FPP1 and FPP2. All right, where does it start getting interesting? What if you have 2 points? Well then, if you have 2 points, then FPP1 says there's got to be a line through them at least. But so imagine that was your entire model. Well, that satisfies once again FPP1 and FPP2. So, but we don't want this. This model is stupid. What if there's like a lot of points, but they're all on 1 line? So you just have 1 line and there's just a lot of points on it. This is going to be addressed in a later video. Well, this model is also satisfies FPP1 because through every 2 points there's a line. And for every